So let's look at a Bode plot example in this video. Now it's a little bit contrived obviously because I want all the figures to work out just exact, okay, but it does give a proof of concept, and it shows how we can build up Bode plots for complicated transfer functions. So first of all, what we want to do is we want to simplify everything, and we want to look at building up complicated function using simple functions. So we'll look at the transfer functions of just a few simple functions, and we can use those to build up the complicated ones. So the first function is just going to be the transfer function g of omega is equal to a constant. So it means that the magnitude of this is just going to be the value of the constant there. So the gain in dB is going to be 20 log to the base to the 10 of that constant. So 20 log to the base 10 of a constant is just a horizontal line. Now the phase is going to be the inverse tan of the imaginary part over the real part. So there is no imaginary part, it's purely a real value k divided by that value k, so that's the inverse tan of 0. So inverse tan of 0 is just going to be 0 degrees. So if I was to draw that out as a magnitude, then it would just be, if this is the omega axis and that's the magnitude there, it would just be a straight line. Okay, and the phase would be a value of 0 degrees. So equivalently, in a three-dimensional sense, these two could be added together to give a three-dimensional picture, which would be a value of omega along this axis. You would have a real value of a function and the imaginary value of your function. So there wouldn't be any imaginary part here because it's sitting at 0 degrees, and it would all be a purely real function. Okay, so that's it drawn out there as a purely real function. There's no imaginary part. Okay, so the next one that we'll look at is the g of omega equals j omega. So the magnitude of this is just going to be our value of omega, and we're going to have the magnitude in dBs 20 log base to the 10 of our value of omega. Now again, if we've seen this in the previous video, but if we were to put in a value of 10 times omega, then the gain in dBs would be the gain of 10 times omega, so it would be 20 log base to the base 10 of 10 omega. And using logs, we can see that it's going to be that's equivalent to 20 plus 20 log base to the 10 omega. So it means that our g of omega, the magnitude or the slope, is just going to be our 20 dBs per decade. Now we've seen that proved in the previous video. And also the phase is going to be the inverse tan of the imaginary part over the real part. In this case here, the imaginary part is omega, and there is no real part, so the real part is 0, so it'll be omega upon 0, which is inverse tan of infinity, which just equals a value of 90 degrees. So if we were to look at the magnitude and the phase plot for this, it would just be 0 up to some value of omega, say omega equals n, and then it would increase at a value of 20 dBs per decade. Okay, and the value of the phase would be 90 degrees, and again, if we were to put that on a three-dimensional plot, we would have a purely real value, a purely complex value at an angle of 90 degrees, and it would just be getting up at 20 dBs per decade. Okay, so it'd just be a line running up here which lies in the imaginary plane. So the final one we're going to need to look at is g of omega equals 1 plus j omega tau. Okay, now this is going to be the reciprocal of a low pass filter, so that's a low pass filter one there, so that's just the reciprocal of it. So g of omega is the same as a low pass, but if it's the reciprocal, then it must be flipped on the omega axis. Okay, so instead of dropping down at 20 dBs per decade, it's going to increase at 20 dBs per decade. equally you could look at it in terms of the logarithms. So equivalently we're saying the log of 1 upon x is equal minus log of x. Okay, so the phase of this here is going to be inverse tan of the imaginary part over the real part. So it's going to be inverse tan of the imaginary part is going to be the omega t, the real part is going to be 1. Okay, so we're going to have our the reciprocal of the low pass. Okay, so it's going to go from 0 to plus 90. Okay, so it's going to go from the 0 degrees up to a plus 90 degrees. Now if I was to draw that in 3 dimensions, you could see omega along the axis, the real part and imaginary part, and the phase would increase from 0 degrees up to a plus 90 degrees, which would be purely imaginary. So you can imagine it going up like this. Okay, and that would be our low pass filter, and you would see this here if you looked in from this angle here. Okay, so that there covers the basic components that we're going to use. Now what we'll do is we'll look at an actual transfer function. So it's a more complicated function than the simple low pass, but again it's a little bit contrived, but it does the task of describing how we can use Bode plots. So let's say the transfer function is given by this here. So it's 2 s squared plus 1, and there's 1, 2, 3, 4, 5, 0 s squared plus 10s plus 10 to the 7s plus, I think that's 10 to the 1, 2, 3, 4, 5, 6, 7 plus 10 to the 7. Okay, so that's the transfer function, and we're being asked to find or draw out the Bode plot, so the magnitude against the frequency and the phase against the frequency. So let's go ahead and we'll see how to do that. So first of all we're going to simplify that, so we can take out the 2s from this, and it'll give us our s squared plus 10 to the power of 4, that's 10 to the power of 4 there, divided by, and this here breaks down into our factors here, s plus 10 and s plus 10 to the 7. So if you multiply those out, you'll get these values here. Okay, so just remember, we multiply it out, it's going to be s squared plus s times 10 to the 7 plus 10s plus 10 times 10 to the 7, which would be 10 to the power of 8. Okay, so that's the bottom line. Now if we wanted to get purely the frequency response, we just replace the s with our j omega. So we're left with our 2j omega plus 10 to the 4 upon j omega plus 10 times j omega plus 10 to the 7. Okay, so now what we're going to do is we've got to split this complicated transfer function here into a group of simpler functions, and we're going to try and write them in terms of our 3 simple functions that we drew out in the previous page. So first of all we've got our value of 2, so we can separate that out. We've got a value of j omega, we've got a value of j omega plus 10 to the 4, and then we've got 1 upon 10 plus j omega and 1 upon j omega plus 10 to the 7. Okay, so we can rewrite that as 2 and the j omega. We can take out our factor of 10 to the 4 there, and that will leave us 1 plus 10 to the minus 4 j omega, and it's going to take a value of 10 to the minus 1 upon 1 plus 10 to the minus 4 times 10 to the minus 7, 1 plus 10 to the minus 7, so that's actually just 10 to the minus 1 there. Okay, and we can take out then, I'll rewrite that as our 2 times that 1 plus 10 to the minus 4, which gives us 2 times 10 to the minus 4 times our j omega times 1 plus 10 to the minus 4 j omega, and it gives us these values here. So you can just check through that yourself and see the arithmetic. So it's just a bit of arithmetic to get it into the correct format. Okay, so what we can do now is we can take these 1, 2, 3, 4, 5 terms, and we can draw them out individually, and then we can go and we can add them together. Okay, so the first one, g1, is just going to be 2 times 10 to the minus 4. So the gain in dBs is going to be 20 log to the base 10 of 2 times 10 to the minus 4, which is minus 74 dBs. Okay, so that's minus 74 dBs there. And we know that it's just a constant, so the phase is just going to be 0. So that's the first part of it done. So we've got our magnitude and our phase plot for the first part. So we just got to go ahead and do that for the rest of them. So G2 of omega is just the J omega. So the magnitude is going to be equal to 1, which is 0 dBs. So the slope is going to be 20 dBs per decade. We've seen that from the previous page. And we can see that at omega equals 1, the phase is going to equal plus 90 degrees. Okay, so we've got this one and that one there, and we've seen that from the previous page. So we'll continue with this. So another 3 of these to go, and that'll be us. So G of 3 of omega is 1 upon 1 plus tau 1 of J omega, which in effect is just a low pass section. Okay, 1 upon tau 1 is 10 radians per second. Okay, so that's it drawn out there, our low pass section. And we can do the same, we can work out the value for our phase, and that's our phase there, just from what we've seen in the previous page. And again, we can do the same thing for our fourth one, is 1 plus tau 2 J omega, which is really an inverted low pass, where the value tau 2 is 10 to the minus 4. Okay, so that's going to be our 10k there, and it goes up at 20 dBs per decade. And this is our phase here, from which we've seen in the previous page. And the fifth one here is 1 upon 1 plus tau 3 J omega, and again that's low pass, and where 1 upon tau 3 is going to be 10 to the 7. Okay, so it's going to be a low pass filter with a cut off at 10 to the 7, which is 1 meg, and the frequency response is going to look like this here. Okay, so I've read through them quite quickly. You can take your time and go back and have a look at the previous page and make comparisons and just check the arithmetic. But what happens is we just add each of those values up. So where we get a plus 20 dBs per decade hits a minus 20 dBs per decade, it would just become a straight line. Okay, so that's what we've got here. Okay, and we've got our 20 dB per decade rise there, and 20 dB per decade rise in this one as well. And the phase plot is going to look something like this as well. Okay, so that's a bit of rough and ready explanation, but there's enough in it to see that we can actually work out the Bode plots from complicated functions, actually using just a little bit of mathematics, a little bit of algebra. So thank you for listening to this. I'll get you on the next video where we're going to start looking at stability with negative feedback. Okay, thank you and goodbye.